new spanning set.
Okay.
Sometimes we say the spanning set generates all of the vector space.
Okay.
I can say it in a slightly different direction. I can say if I got a spanning set, then if I look at every possible linear combination of the elements in the spanning set, that would be my vector space.
Okay. And so, I guess the part that I was a little confused with there, so when we're figuring out if they're collinear or if they were nonlinear, right? I think I got my terms right, I might not, but we plugged them into a determinant in order to see that. Can you explain to me why that would prove that they're...
No, because I have no idea what you're putting in determinant.
Okay,
What's
so...
linear? An element of two space?
So let me grab you a problem here.
You meant linearly dependent on the vector.
Yeah, I'm going to read this so I can make sure my terminology is correct. So determine whether the given set of vectors spans R3, and then they give you a spanning set, basically. And so in order to determine whether it spans R3, you put it into a determinant. Coplanar, okay. So they're coplanar if, and only if, the determinant equals 0. And
That would mean they're dependent.
non-coplanar, I guess is the other one, right?
They don't live the same plane.
If they don't live on the same plane, okay. It's a little weird. I need to work on this. And so all we do with those ones is just plug them into a vector, or a determinant, sorry.
So can I bring one up, you guys?
Some of these other ones are weird, yeah.
Sorry, I can't
Yeah.
find it. In section 4.2,
Okay.
exercise 11. If you don't have your book, can I just read it out loud? It's only 2 short sentences. So let P denote the set of all polynomials whose degree is exactly 2. Is P a vector space? Because a student just asked me this question just, I think, 10 minutes ago. And he said the answer back in the book's one thing, but I came with a different answer.
Okay.
Daniel?
I said no because you could get a polynomial that just is to the first degree and it asks exactly second degree. So.
Okay, that's fine. I just would have said it's not closed under scale multiplication or even vector addition. Because if you take a polynomial exactly degree 2 and you multiply it by 0, you get 0, which is a polynomial of degree 0, not a degree 2. Or you could even attack the fact that that set of all polynomials whose degree is exactly 2 doesn't have the 0 element in there. So it can't be a vector space. I've got to have a 0 element. So I think there's lots of reasons why it's not a vector space. But someone told me that the solutions manual says it is a vector space. So just be aware of that.
Okay.
I didn't mean to interrupt you, Brown.
Oh, no.
So are you guys feeling okay about spanning sets, Michael?
I was wondering if you could go over number 7 and 19.
What section are we in?
4.4.
7 and 19?
Maybe 17.
Okay, you're creating a list. I can't
Okay.
remember the numbers. 7, 19, you said Brad.
17.
Oh, look at that, they're all prime numbers. And if I take a peek at number 7, I want to show that this set of vectors does not span all of R3. But it does span the subspace of R3 consisting of all vectors lying in the plane whose equation is, don't worry about it, I'll give it to you when we get there. So, to show that it does not span all R3, what do I do? What do I do?
A1 and A2.
Well,
Find if they're linearly.
see if the
Well,
determinant,
actually-
you could see if the determinant equals 0 or not.
We can go there. I like what you're saying, but I haven't really done anything with linear independence yet. And because the author asks us in this section, I assume, he assumes that you haven't seen it yet.
Okay.
But you're right, because it's an R3, that was really good. Because I'm in R3, then having three vectors will span all of R3 as long as the set is linearly independent. And so you could check that. And so I just maintain you could do this. Take an arbitrary element of R3, like, how about this one? How about X1, X2, and X3? See if you can express this as a linear combination of these three vectors. Am I writing down the wrong numbers, you guys? I'm
No, I
sorry.
think you got 3, 4,
Yes,
5
3, 4,
there.
5. They overlap at their end.
Yeah, they overlap at the ends, yeah.
These overlap at the endpoints, but not the other ones. Can you help me with this?
4, 5, 6.
I'll listen. So I maintain if these three vectors span all of R3, then an arbitrary, bless you, element of R3 can be expressed, bless you, as a linear combination. So let's find out what C1, C2, and C3 look like. If I were to put this in a determinate form, wouldn't I get this? Is that a 1, 3, 4 is X1, 2, 4, 5 is X2, and 3, 5, 6 is X3.
Mhm.
Let's see if we can't solve for those coefficients C1, C2, and C3. And solve for them. I think that gives me this equivalent matrix. Maybe not that one. How about this one? Ay.
So is there an easier way of doing this aside from just plugging them into the matrix, or is the matrix the easiest way?
You know, sometimes if you understand determinants, you can use determinants to see if you've got a unique solution. If you got the right combination of equations and unknowns.
Okay.
And I think my third row becomes this. You guys, I'm sorry I'm so slow.
That 0 plus X is 3. 0. Sorry.
That is a 0, yes. I'll pay attention to my own writing. So everybody, moving in the second column, the force that entry along the main diagonal to be a positive 1. What do I do? We gotta test this week. Let me ask the question again. We can test 2 days from now. To force the entry in the second row, second column be positive.
Divided by negative 1/2, or multiplied by negative 1/2. But, yeah, the third row is...
So to
is
force
the-
that negative 2 to be a positive 1, don't do anything. I think for free, if I merely take the second row times negative 2 and add it to the third row, use the results of my new third row, my life's just a heck of a lot easier. Do you guys see my point?
Mhm.
And I think that generates 0, 0, 0. Okay, I'll slow down. I said negative 2, so that's a positive 4x1. Oh, minus 3 more. Minus 2x2 plus x3.
Which
What
is...
the heck does that say?
Well, since the actual equation on the plane is x minus 2y plus z equals 0, and that equals 0, then doesn't that mean that it just spans it?
All your X
Yeah.
equals 0?
Right, X minus 2.
I don't like what you said. You said it was correct, things correctly. But I don't like how you attack that second part of the question. I just want a straightforward answer to this question.
Okay,
Do these three vectors span all of R3?
yes,
No.
See, I think the answer is no for this reason.
okay,
Because I think if I were to write this out in equation form, 0 equals this garbage.
okay.
That means x1 is equal to 2x2 minus x3. I see a tight relationship among these quantities. They're not free anymore. And I wanted to see if arbitrary elements up here can be expressed that way. And so I think this forces some kind of constraint relationship among those quantities, x1, x2, and x3. I mean, that's how I would have looked at it.
So there's a relationship between them, so that means they're not spanning.
Yeah, that means they don't span all of R3. They're not free.
Okay.
They're not expressed free variables. I mean, if x3 is t and x2 is s, then x1 is going to be expressed in terms of x2 and x3. Now, I have to confess, if you guys want to talk math 32, I guess I'm being silly with my subscripts. This really just says x minus 2y plus z is equal to 0. That is the equation of one. And I do think that's the second part of the question, I think.
Yeah.
Number 7?
Well, it doesn't, it shows that the set of the vectors does not span R3, but does span the subspace of R3 consisting of x minus 2y plus z. That's what I meant when I was,
okay, then
yeah.
I'll agree with that.
okay, I'm sorry.
The
I
reason why I'm
didn't phrase it
nervous
right,
about even saying that much is
Yeah.
that kind of applies, you're saying to yourself, I understand that subspaces have certain relations to the bigger space, and they just haven't talked about that yet.
Yeah, because to show that it spans all of R3, right, you could just throw it into a determinant, and
Yes.
that doesn't even matter at all, right?
I agree.
Okay.
You guys, why don't we just talk in this direction? Since he brought it up. If I live in 3 space, what's my dimension? What is my dimension?
3.
With your intuitive notion of dimension. So it's 3. What kind of subspaces of 3 space can I have?
With our intuitive notion of
2 and
dimension,
1.
what does that mean?
Why did you say the dimension is 3?
Because it's in 3 space.
Thank you. That's an intuitive notion.
So is there another answer to that, or is that just...
Oh, heck yeah. As of
Alright.
today, we're going to think of dimension of a vector space as a number of elements in its basis.
Please tell me it's not gonna be 1.
Oh, it can be. Yes, it can be. In this course, however, we're only restricting our attention to finite dimensional vector spaces. We're not going to look at infinite dimensional. Well, I take that back. We do take a glimpse at infinite dimensional vector spaces, but very much just a glimpse.
Okay.
So, I don't think anybody answered my question. What kind of subspaces can I have in 3 space?
R2 and 1. Or not
What's
R2.
R2?
Doesn't it matter what?
2 dimensions and 1 dimension.
I don't know what you would call it. Like, if it's a matrix versus a polynomial.
Completely irrelevant.
Oh, really?
Because like I said before, I'll prove to you that I can transform into this just standard vector spaces.
Okay.
Rn, I should say that, not standard vector spaces, Rn. So, wait a minute, what are the subspaces of 3 space? I still haven't heard the correct answer.
Equals whatever it's there.
Well, it could be all R3 space. Any vector space is a subspace of itself. Give me another subspace.
2 space.
But what do you mean by that?
By only 2 elements of all the elements in R.
So you're saying a plane?
Space. Yeah, a plane.
See, I disagree, because I
Well,
don't
would a
think
plane be 2 space? A plane, or a line would be 2 space, right?
Well, a line is 1 dimensional. A plane is 2 dimensional.
Plane is 2 elements out of the 3 space, right? That's what you're saying.
Okay.
Yes.
Okay.
So I maintain a plane is not necessarily a subspace of 3 space because it doesn't necessarily contain the 0 element. So you really meant a subspace of 3-dimensional space is a plane that passed through the origin. A 1-dimensional subspace of 3 spaces, a line that passed through the origin. Yeah, it's not the 0 element. Is the empty set a subspace of R3 of dimension 0? No, because that's empty. A subspace has got to be a non-empty set.
Okay.
Do you think there is a 0-dimensional subspace of R3?
Wouldn't that just
What, I'm sorry.
would that be the origin?
Perfectly put. It would be the singleton set containing the origin. That would be the 0-dimensional subspace, the only 0-dimensional subspace of 3 space. Excellent. Yeah, that was good.
Would you maybe be able to do 9 also?
I hope I'm able to do number 9. So, express. Okay, everybody, check this out. Sorry, I keep losing my numbers. Okay, this is a little bit different. The author's telling me that the set of these 3 vectors does span all of R3, and he wants me to express the arbitrary vector v bar whose entries are x, y, and z as a linear combination of v1, v2, and v3 bars. And those are the v1, v2, v3 bars. So, my apologies. The question is different from what I just said. He's asking me to show that these 3 vectors span all of R3. My apologies. I read that incorrectly. And you guys, I'm going to apply the same tactic. I'm going to come in, see what happens when I force an arbitrary vector like this, although he called it x, y, and z, who cares what you call it, as a linear combination of those 3. Nothing happens. This time, however, unlike my last example, I'm going to generate the following Augmented matrix, oh, I can't. Okay, you guys tell me, I don't have my glasses on. Negative 1, 1, 1, 2?
3.
Excellent.
3 negative.
3, negative 2, 1. And 2, 1, 1, thank you.
Wait, huh?
Are you, Alex, you see where I'm getting this?
Yeah, did you transcribe them correctly?
Let's just pick the first element of each one.
I did.
Yeah.
And Alice, check this out.
Okay.
Tell me if I can get away with not writing this. Take that first vector, put it here. Take the second vector here, third vector here. I'm just equating first components. So the sum of these three is going to be equal to x1.
Okay,
So you see it?
I guess.
And in solving for this matrix, it's in solving. I'll slow down. In reducing this matrix, does that give me a 1, negative 1, negative 2, negative x1? Does it also give me a 0, 1, 7, 3x1 plus x2? And then does it give me a 0, 3, 5, 2x1 plus x3? Now, a little bit of the work is done for me.
Oh,
Yes.
sorry. No, I was just looking at those numbers and it wasn't making sense, and then I realized that that's a different problem.
My
All right.
apologies, I can change them.
Sorry.
And now, since the work's done for me in the second column along the main diagonal, I'll work elsewhere. I will take that second row, and in my head, I'm going to multiply it by positive 1, add it to the first row. 3x1 plus x2. So add in the first and the second. Quick, I'll slow down. Is that a 5? And then a 2x1 plus x2? And then, if I multiply the second row by negative 3 added to the third, get a couple zeros as desired. Yikes, what is to rest? Is that a negative 16? I'm just really slow today. Is that a negative 9x1? Minus 3x2. Plus my x3. Plus 2 more x1s is going to give me negative 7 x1s in the end.
Divide it all by negative 16.
I will. And my very last step is to clean up what the heck remains in that very last column, which is indeed going to give me the identity matrix to the left of the vertical bar. Here's what's down below. You guys, you relax, let me do the arithmetic for you. I think in the second row, I'm going to generate... I said, let me do the arithmetic for you. I take that back. Is that negative 49? Ay, ay, ay. Plus...
I
oh,
have
come on,
a
isn't that
calculator
nice?
that can do fractions.
What's that?
I said, I have a calculator that can do fractions.
You can do them on a desert island.
Well, no, on a calculator. If I had my calculator on a desert island, I could do
Yeah, but if
fractions.
you're on a desert island, you don't have a calculator. You got to put long.
Well, what if I brought it with me?
Your batteries are eventually going to run out.
It's solar powered.
The weather is not always going to be sunny.
It also has a red hand mark on the back of it. It
Ay,
talks to
ay,
it.
ay.
It's like Wilson.
Exactly.
It's not a red hand mark, though. I drew like pie and blood.
You guys are so trustworthy. It's nice.
It'd be great for Halloween.
the heck does this say?
It says that your basic. Well, if you look at your ones, then you've got your C1, right? Or yeah, your C1 up in the top there.
You guys, when it comes to so much writing, can I write what he's saying?
Yeah.
Can I get rid of this?
Sure.
So I have to rewrite it.
Sure.
I think that very first row says, now this is my choice of words in English. I think the very first row says that C1 can be expressed in terms of x1, x2, and x3. C2 can be expressed in terms of it as well, so can C3. That means it doesn't matter what x1, x2, and x3 are, I can always find the C1, C2, and C3 values, assuming that I can express any vector in R3 as a linear combination of these three. Unlike my last example, I think that's why this is telling me that my set of vectors spans all R3. Do you guys agree?
And so, how would you actually, as a linear, and express V equals X, Y, and Z as a linear combination of V1, V2, and V3? How would you like your answer phrased for that? Like, if we just showed you that, would that be sufficient, or would you want us to write it in like set notation or something like that? Okay.
Doesn't that answer the question?
Perfect.
So x1, x2, x3 is equal to the linear combination over there where C1, C2, and C3 are given as such. And I think the way I'm saying is beautiful because now, depending on what x1, x2, and x3 are, I can find my C1, C2, and C3.
Okay.
And I can find those such CIs no matter what x1 through x3 really are, numerically speaking.
Okay.
I think it's that smooth.
Is that an X before C2?
Sorry, it's a plus.
Oh.
Dan, I was trying to be lazy. Sorry, it's my fault. I'm being too lazy. So, if you guys want me to take a peek at something like 17? So let S be the subspace of M2 consisting of all skew-symmetric 2x2 matrices. So S is a collection of skew-symmetric 2x2 matrices.
17.
So you guys, what would that look like? It'd be an A sub 1, 1, A sub 1, A sub 1, A sub 1. I keep saying we got the test coming up this week. No, how about nothing? If it's going to be skew symmetric, I think I should have. Such that A range is over. But jeepers, this is nothing more than a vector space scanned by a set containing
Matrix 1, 0,
0, 1.
negative 1,
Negative 1. 0. I agree.
Multiplied by A, right? Or
I disagree because when I use a span notation,
Oh, okay.
I just want this generating set in there.
so, just 1 second. So what the book did is they rewrote the set notation as A multiplied by.
No, I like that.
Yeah.
So you put an intermediate step in like this.
You put an intermediate set by rewriting the set notation.
And I sometimes do as well.
Okay.
But if they're going to use a span notation, that's the way to go.
And so if we skip that part and just went straight to the span, would that be right?
I'd be very happy.
Okay.
What about 19?
An element of. Talk to Valga after class about maybe doing the symbolic logic lectures for calculus club.
Right. Or put it on the test.
Yeah, I think a lecture would be better, because it's already going to be on the test. You gotta be able to write using symbolic
Wait, what
logic
did you
with this one. Randall and I are going to talk about that after class.
So everybody,
Symbolic logic lecture.
determine the
for calculus
span.
club.
Oh, I was
What's gonna be on the test already?
A table.
Oh, no, not a table.
And describe it geometrically.
That's right.
Oh, well, ask.
Well, I think it's gonna be a subspace of R3, so it's either gonna be a plane or a line. Which one is it? You took too long. Which one is it at a glance?
It'll be a
Plane.
plane,
How do you know this so fast?
because there are 3 elements.
That's not the reason.
No, because there are two.
Wait, I thought you took too long.
2 points. No, not one of the points, but what are?
Well, there are 2 points, but there are 3 coordinates.
No,
right?
I like the way you stall. I don't know what you, I don't know how you wanna think of this. You can think of it as points or standard vectors in tree space.
Yeah.
I know in the math classes and in your physics classes up to now, they're different. But as far as you and I are concerned, we're treating them to be the same. And you can just give me a little bit more longer, and I'll prove to you they're the same.
Is it because they're not collinear that they make it fun?
What do you mean collinear in this case?
That they're not.
Because any 2 points are gonna be collinear.
That the vectors aren't linear, like one is in a linear combination of the other,
One's not a
multiples.
multiple of the other thing. You said it correctly with linear combination. It's just that if you have 2 elements, you can tell for free whether or not they would form a line just by seeing if one's a multiple of the other. And since one's not a multiple of the other, I think for free, I know I've got a subspace of R3, which is actually a plane passed through the origin, not a line. Do you guys see
Yeah.
my point?
So, really weird question, but
Yes.
it's just kind of confusing me. Why are the vectors written like that? Why aren't they in proper vector notation with the brackets that we'd use for vectors? Why are they written like points?
Up to this point, what difference does it make? How you add 2 points can be the same as you add 2 vectors.
It shouldn't make a difference, but I mean, we've been trained and conditioned to write them a certain way. And
Oh,
I'm just
right,
wondering
right,
why.
but this semester I'm training you from all that you learned.
Well, why did you train us in the first place?
Because of the applications of other things. You guys check this
Okay.
out, watch. Haven't we been lying this whole time? I mean, with the standard addition operations and scale multiplication, isn't the way you and I treat all these things really the same? I just think the position of 1 and 3 in this 2x2 matrix, or maybe depending on which one's being multiplied to x or I, is just a placeholder. And so I think the underlying mathematics is indeed the same. And I will, in the near future, this semester, build a one-to-one onto linear transformation from one of these vector spaces to the other to show you that they really are indeed equivalent in some general sense of what it means to be equivalent with vector spaces.
Okay.
So yeah, that's why it does make a difference.
Okay.
We haven't answered the question. How do you determine the span? What would the span look like?
You would have to multiply a constant by v1, right? And then add a constant multiplied by v2
So it would look like a C1
times
plus
v1.
2C2, comma, negative C1 minus C2, comma, 2C1 plus 3C2.
Yes. Is that it?
I don't know, I'm asking you. Well, one.
Do we separate the constants?
Yeah, you'd just be going backwards. I was just going in the forward direction. Michael?
Why is it arranged in that fashion where it's C1 plus 2C2? Like, where do those numbers come from?
I was looking at C1 times the first plus C2 times the second. So the very first entry is going to be 1 times C1 plus 2 times C2. There it is. Second entry is going to be negative C1 minus C2. There it is. Do you guys not like this?
In the book, different ways that the vectors exist in R3 before you decide this. I don't know if that's important.
It's definitely not important here, only because of the notation I'm using. I opened a 3 tuple, and so I think it's for free. well, how'd you do Math 30? Or are you current Math, I said 30. How did you answer this question, Math 32? Or you current Math 32 students can answer the same question? How do you generate the subspace? In Math 32. I could look at something familiar in 32.
Have we even gotten to that yet?
Yesterday in class.
Oh, yesterday. With the planes? Oh my god. I haven't done the homework for yesterday yet.
Anybody?
Didn't you let X be the first, Y be the second, Z be the third, and then try and form a relationship?
You know, that's,
X, Y, and Z?
I do that when I already have the equation of the plane.
So,
Oh my goodness, so for you 32 students, you have an exam next week, right?
Well, that's what this weekend is for, is studying for next week's exam. This week is for studying for this week's exam. It's like, I study really hard for one exam, and then I just have another one coming up right after.
From him, no less.
Yes.
Okay, we got 2 points. Can't we, I don't know, add them together, get a third point? Still in the plane.
Okay.
And then maybe take 2 points at a time and look at some directed line segments. And then look at the right-hand thing.
Cross
Cross
product.
product to get a normal vector to the plane. And then use standard form A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals zero.
Yes.
Did I walk in the right room? Did I just speak a foreign language? I did, sorry, Alex. Just out of curiosity, how many of you had taken 32 already? So the vast majority of us, okay. There's only a few of us who have. What's
I was
next?
told it was a requirement.
What's that?
I was told it was a requirement for this class.
Oh, who told you that?
It's not
My
required.
counselor.
Oh, no, it's definitely not.
You should probably
Even
take
the
it.
catalog or go online when we list a course, we clearly state that we recommend 32, but it's not a prerequisite.
It's strongly
Probably why
recommended.
you didn't have it.
Yeah, one of the main reasons we need to do something like this because, well, all of you know this because you're in Math 33, but it takes so long to get through the math sequence. We try to find places where if you needed to, like with trigonometry and college algebra, or this class in Math 32, if you can double up, we want you to have that opportunity. Yes?
So with that span, is the reason, so why can't you write it in a form where it's span and then set? Can you write it in the same form as you did with the previous problems? That, you know, obviously the previous problem was a matrix, and this was not.
No, that doesn't make any difference. I mean, that's the notation I used before. I just think it's kind of silly. I'm just restating what I had up there. Nothing. So you guys, are we done? Do I get to talk today?
Sure. Did you write that